in the next week or two, I'll really have my you know what together here, and we'll be able to start a lot faster. Have your clickers ready. We're going to do some demonstrations. You can see in the back over there the Van de Graaff generator. And if you washed your hair last night or this morning and didn't put any goop in it, or not too much anyways, then it might, we'll see if your hair will fly out into the universe. But we have some other stuff to use to demonstrate that in case. Now, before we start with our normal physics, I just want to make a mention. Today's a somber date, September 11th. And 18 years ago, there was a terrorist attack in the United States. Most of you guys were little shrimpy kids at the time. So you don't remember what it was like. Maybe you remember your mom and dad being, or your older brothers and sisters being affected. And I grew up in New Jersey, so for me, these are familiar views. For instance, I know that that's the Brooklyn Bridge in the foreground of that picture. But I was not in New York at the time, and I just want to tell you a little bit about what I experienced. This is the campus at University of Vermont at the time, and up in Burlington, Vermont. That's Lake Champlain in the background. And I was teaching physics there. My office was right in this building, right about where that arrow is. And the reason that I bring that up is on September 11th, I was preparing for recitation up in my office, up on the 5th floor. And it was a warm day, so I had the windows open. And when the windows are open it was a beautiful day. And when the windows are open there, you get a breeze, if the breeze is blowing right. But you can also hear everything out at the airport. Now, one of the things out at the airport is the Vermont Air Guard, the National Guard. And you can always hear those guys taking off at the airport. You can't hear the commercial airliners, but for some reason, those F-16s are really loud. I guess they don't care too much about civilians for noise, but you could always hear them. And I remember that morning, I usually get there about 7 and get my lecture notes ready and my recitation notes ready. And I remember hearing them. I thought, oh, they're out there taking off today. But I didn't think anything about it because you hear them all the time. They're always, doing drills of various kinds, taking off, landing. But that morning, I was in my office and I heard them occasionally taking off. And I got a phone call about this time. My wife told me, Thomas, there's been some kind of attack in New York City. And she told me that there was an airplane that crashed into the World Trade Center. And so what I did was I put everything down and I went downstairs to the 4th floor by the main physics office. And across the hall from that was a meeting room for like seminars and stuff. And they'd set up a television in there. And right across from that room was the classroom where I was supposed to be meeting at 10 o'clock. So I went down there and started watching the television coverage. Who was old enough to have remembered the stuff on TV? A few of you? Okay. And so I was watching, and my students came to the door and they said, Dr. B, are we going to have recitation today? I said, no, not today. But if you want to come in and watch, so a lot of them came in and watched the news. And we were all trying to make sense of it. And apparently they think that there were some other planes that they were going to try to get. You know what supposedly they were going to try to destroy? The World Trade Center, the Pentagon, and Congress. And then the other one, they were going to try to get Disney World. Did you know that? Yeah, supposedly. Big landmark, easy to hit. And I was talking to my students at the time. I think they're going to try to get Disney World next if they haven't already. because it's the only big thing on the East Coast that has symbolic value, like the World Trade Centers. Anyways, we were talking about that, and I remember telling my students, I heard all those jets taking off. Now, Vermont is in a perfect position to try to chase down those terrorist airplanes. So I've never figured it out whether those guys on that day were in a chase. There were other planes that were in a chase to get down there and intercept those planes, and one of them did get intercepted in Pennsylvania. But it was a bad day, and I want you always to, for those of you that were too little to remember or to think about it or to experience it, it was a bad day. But we right now we've rebuilt and stuff. And I grew up in New York City area, and there's the World Trade Center. They're enormous buildings. They were enormous buildings. They're bigger than any. Take the biggest buildings here at UCF and squeeze them all next to each other, and then you've got the footprint of one of the World Trade Centers. They're just enormous buildings. And I couldn't believe it when the first one fell down, and then the second one. It just was, and then there was a big hole after they cleared away the stuff. And I've never been up there since. I've always wanted to go up there and walk around and take a look around. But I went to New York University in Greenwich Village. That's where I got my bachelor's degree. And I used to ride the train in from New Jersey with my dad. My dad worked a few blocks away at the time. He was retired in 2001, but at the time when I was in school, he worked a few blocks away in the financial district down by the Federal Reserve Bank. And so we'd ride the train in together, and we would get off at the World Trade Center and then get onto the New York City subway train and go uptown. I would go uptown, or sometimes I would walk. So I've walked around been all around the World Trade Center. My dad used to take us, didn't used to, I mean, a few times he took us to breakfast and brunch, I guess, at this very fancy schmancy restaurant at the top of the World Trade Center called Windows on the World. Oh my goodness, you have to wear a suit to go in there, and a tie. And but we went in there for brunch a couple times, and it's really nice, but it's gone now. You could look out over the entire harbor. It was really beautiful. Really expensive too. But I had a girlfriend that worked up in the World Trade Center. A lot of friends. And she wasn't on one of the casualties. She had moved on to a different job by that time. But it was a bad day. We got to remember and hopefully that never happens again. We want to keep our guard up. All right, so that's enough about September 11th. And let's get back to the concepts that we left off with last time, electrostatic field concepts. And we were talking about the difficulty, the ambiguity in the forces and energies of that simple charge array that we had, 2 protons, and forming a right angle with the 2 protons was that 1 electron, and we were figuring out, it had a net force to the southeast and stuff. And this is one of the problems in the Coulomb interaction that you don't get in the gravitational interaction, because the gravitational interaction is a lot simpler. There's no repulsion in gravity. It's always attractive. But the electrostatic interaction, the Coulomb interaction, has both. And so as a result, with things that are electromagnetically organized, like crystals, and even a diamond has a very simple tetrahedron shaped crystal, or it's based on tetrahedra. You can have very complex structures. Here's another one, extremely complex, DNA. the double helix, and it's enormous. Now, versus things like planets, the things that are dominantly controlled by gravity tend to just blob together into spheres or as close as a sphere as they can get. Now, this is the dwarf planet Ceres. It's out of the asteroid belt. It used to be considered an asteroid, but we now consider it a dwarf planet because it's a certain size. And you can see that it's not perfectly spherical. It's a little oblong. But that was the first of the asteroids to be discovered. But very simple. And, being an astrophysicist, I don't have to worry about crystals and stuff. I only have to worry about spherical symmetry for the most part. It makes life a lot simpler. But the Coulomb interaction make a note, Coulomb interaction introduces complexity as opposed to the gravitational interaction. There's plenty of stuff about gravity that make it tricky, but not the way that it organizes matter. It tends to organize itself into, if the clump is big enough, it'll turn spherical or pretty close to spherical in the case of Ceres. Another thing that's difficult is that you have pluses and minuses. It's this part and parcel of the same thing. You have attraction, repulsion, and with that comes pluses and minuses, positive charges, minus charges. So that means that, like, for instance, if the net force on the electron is here, that means that in this direction, just to the southeast of it, you're going to be generally getting larger kinetic energy. In other words, if you start at rest up there at the corner, you're going to develop some speed in that direction, at least to the outset. All right, because that's the net force at that position. Now, the problem with that is, as we talked about last time, if you have a proton there, it's completely opposite. It's going to want to move away into the northwest quadrant, and it's going to find more kinetic energy off to the northwest. All right, and so that's part of the difficulty, and because the way to figure out really difficult physics is to use energies and not F equals ma. And for those of you that were in my Physics 2053 class last spring, you may remember that I mentioned that a time or two, maybe more than that a lot of problems are much, much easier when you apply conservation of momentum and conservation of energy. They can be done using F equals ma because they're equivalent, but sometimes the force view is much trickier to use than the kinetic energy or the energy and momentum view. And general relativity, which is what I specialize in, is all done in the energy momentum view. We don't really use we make results, and then the last thing that you do with your calculations, you get your model built and everything, and then you say, all right, well, what would a typical force be over here? 20 light seconds away from the event horizon, or what have you. But before you leave that as the last detail, not as the first detail. And quantum mechanics is the same way. Using quantum mechanics, the only way to make really good, easy sense of it is using energies and potential energies and kinetic energies and so forth. In this example, your apparatus is the electron. And that's an important point for us. What we were trying to do, our target particle, when we were studying this last time, this is kind of a symbol that I mentioned last time. All right. This little array here, a right angle array. And the apparatus, the target particle or the apparatus is a net negative charge. All right. And so, but if you have as I said, if you have a proton there, the proton would want to go off that if that's your apparatus, or a net positive charge to your apparatus, then you're talking the opposite. So that's a difficulty. So how do you deal with that? And what I'm gonna go through with you is the abstraction process to deal with that. So what you do is you abstract your apparatus out of the picture. So proton, gone. Electron, gone. And so what you do is you abstract those out of the picture. You keep your two source charges there. And then you replace them by a geometric point, and you study the effect of the electric field or the electrical effects at that point, and it could be any point you want, due to charge 1 and charge 2. So the effect at that point is controlled by what we call the source charges. Okay, the charges that make up my system that I'm trying to use an apparatus to measure the system of charge 1 and charge 2. So my physical system that I'm studying with an apparatus, I've abstracted out the apparatus. Now I just look at the physical system. And I study the geometric points. And notice that it's the same. Those two pictures are now identical. All right. When you had a positive apparatus and a negative apparatus, the previous slide, this one over here, no, you don't have, those aren't identical, and you've got a lot of trouble. But if you abstract them away and replace them by just considering the geometric point, then you make yourself, you considerably simplify your considerations and your math as well. So the effect there at that geometric point is called the electric field. All right, we're going to be talking some more about that. And so go ahead and make a sketch of this, all right, for your notes. This is the same one we had last time. And I'm just using it as a generic example, you know. And I'm going to extrapolate to more generalized stuff. Daniel. The reason I focus on you is because you're right in front of that screen, so it's all right. But I know Andrew's sitting over here with his back to me. See, he's focusing on that. Anyway, so this is your diagram, but you know, it doesn't require that you study that point up there. I mean, you can, you know, like here's another point down here in the lower right. You know, so do the trig here. And if that's the point that you want to study, and if that's where, in other words, if that's where you want to put your apparatus, okay, whatever your apparatus is, do the trig down there. Or, you know, you move it up here. You know, you want to put your apparatus up here, you do all your calculations up there. Or you want to move it a little bit down here, no problema. Now, the trig is a menace to society, but you can do it. I mean, it's just sines and cosines and components and stuff. So it's not too bodacious. Now, I'm going to ask you a clicker question here. All right. And this is going to be a clicker question with an open answer. All right. In other words, you could type in letters and numbers. And we're going to collect that, and I'm going to look at it later. But what I want you to do is to talk with your teammates, if you have any, if they're not absent. And if you don't have your regular teammates, team up with somebody else. But talk with your teammates, and then I'm going to ask for somebody to stand up from your team, if you volunteer, and render a verbal explanation of your answer to this question. Where is the electrical effect 0 for this array of source charges? All right, so take a few minutes to talk it over with your neighbors. Make some diagrams if you want. Add to the diagram you have. And let me start the question. We're on frequency AB. If you're using the clicker for the first time, hold the power down until it flashes, then type in AB. And just type in a word or, or but definitely talk it over with your neighbors. You guys can circulate around now. Oh, I'm starting to get answers. I thought this would be tougher, but let's see what you guys got. 2 minutes. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, I see some interesting answers here. I'm not going to display. I'm not going to display the answers yet. But I would like to ask for a volunteer to step up to the screen and use either the left index finger, the right index finger, or the left index finger if you're lefty, to point to the position in space where the electrical effect is 0. Who wants to volunteer to do that? Raise your hand if you're bold. Okay, we got one volunteer. Who else wants to volunteer? You want to volunteer? Wait a minute. I want to see who else wants to volunteer. Because we might need a backup volunteer. Okay, what is your name again? Brett. Brad. Okay, Brad, go to that screen over there. Brad's going to volunteer. And then we're going to ask somebody else to make an explanation. What was your answer, Brad? The midpoint of 1 and 2. Thank you, Brad. Well, you know, you weren't really pointing at it, it's to my opinion, but it's close enough for government work. Okay, Brad, go ahead and sit down. Who wants to stand up in place? And that is correct, the midpoint between those 2 point charges. Who wants to render a verbal explanation of why that is true? You don't want to? Who wants to? Somebody, come on, somebody be bold. Because, you know, the thing is, I see it. I see it. The thing is, you want to be able to talk about this stuff because talking helps you learn how to think, especially if you're talking in a room of your peers or in a room with peers and experts. And experts are up here in the front. But you guys are junior experts, becoming experts. All right, who wants to stand up and hopefully not make a total fool, maybe a semi-fool of themselves? No, I don't want, you've already, you want to do it? Who over here wants to try it? Daniel? No? Daniel, you've already done it. Krishna, you go ahead. Everybody listen to, stand up, Krishna, please.
Hi guys. All right. So basically, what we were saying is that both of the photons, they're the same charge first of all, but they're at different distances. The one at the top is 4 nanometers away, and the one at the bottom is 4.5. So what we were saying was that at a point where both of them are equidistant from each other, which in this case would be the middle of the hypotenuse, would be where the electrical effect would be 0.
What do you think? A for the day for Krishna. Very good. Okay. That's a good explanation. Did you take notes? You want to say it again? You can't repeat it? Well, it'll be on YouTube. So I hope that got repeated onto YouTube. Now, I'm going to ask you another question. Follow-up question. And you know what? I don't need to show you the answers here. There's a lot of people with good answers. There's a lot of different ways to say what, basically the midpoint. Now, my next question is, I want you to listen carefully. Is that, and this is multiple choice, so hit the refresh key on your calculator. Hit the blue refresh. And now we're just going to type in an A or a B. A for yes, B for no. The question is there any other point where the electrical effect is 0? A for yes, B for no. Dee, 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 dee. Yes or no? Is there any other point? Yes, there is. No, there isn't. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh-oh, we got some splaining to do. We got a mixed bag here. The majority say no. The majority says no, and the minority says yeah. Um, all right, let's get a positive case. For those who say yes, what is your answer? I mean, if you're not guessing, I mean, just, A or B. If you have a reason. See, because what I want you to do is I want you to think, and I want you to be able to render an explanation. If you're going to med school, and if God bless you, you become a doctor working with real patients, you're going to have to render explanations that are based on your thoughts and true concepts and physical measurements like blood pressure and stuff. Right? So you're not going to have to answer about this stuff, but we're developing that skill. So who wants to give me who that answered yes can stand up and render an explanation for their answer? Now, people that have already done that, I don't, I'm going to bypass you because I want everybody to be able to, get into this stuff. So I'm looking for maybe for somebody from that table back there, or maybe from that table back there. See the people in the corners, you know, who answered yes and wants to explain why they answered yes. I see your hand. I'm trying to distribute the grace here. Okay, go ahead.
I said yes because
Wait a minute, you have to stand up. And you have to say your name.
my name's Cheyenne.
Cheyenne.
I said yes for like if they were equally just on the outside, it's the opposite direction.
Go to the screen and kind of describe it there.
If that was the midpoint before, I think it would be also if they on the opposite if they moved out more.
You mean on the other side of number two?
Yeah.
Anybody agree with that? I do not agree with that. Because if you go on that diet, if you take the hypotenuse and keep going past number two, somewhere out that way, is what you're saying?
Yeah.
That's not going to work because listen, if you're on the hypotenuse and you extend it past two to the northeast, and you're out there to the northeast along that hypotenuse direction, you're gonna have more of this. You're gonna have more northeast newtons out there. It's not going to be zero up there. But that is the correct answer. Yes. And those of you that answered no on that one, you got caught napping. Oh, okay. So you guys are giving high fives. How about giving an explanation? See, because you cannot trick Dr. B forever. Do you want to give an explanation? You cannot? So it's all right if you guess. I mean, guessing is okay. And sometimes guessing will save a life. But who answered yes and can give an explanation? All right, you can stand up at this table, and you have to tell us your name.
Oh, hi, I'm Thomas.
What? I'm Thomas.
I'm
So, so that's how it's going to be then, huh? Okay, good. All right, Thomas, go.
Alright, so I actually, I put no, but then I thought about it for like 10
What?
seconds. I thought about it for 10 seconds and I realized it was yes. Because if we're using the logic that putting the point in the middle of the hypotenuse due to the forces being equal will zero it out, then if we put the point somewhere where it's equal distance, anywhere equal distance from the two protons, then it will zero out.
Okay, sit down. You stand up. Yeah, I'm forcing you to stand up. Why are you nodding your head?
Because we kind of like went off the same thing.
Talk this way.
Yeah, we kind of went off the same thing.
Oh, you can sit down. Wait a minute. What's your name again?
Paul,
Paul. Okay.
if both charges are equidistant, kind of went off the same thing. If you can pull it out more and it stays equidistant, I think it would just cancel out.
Okay, Paul, go to that screen and demonstrate where those other points you think would be.
We thought that it would be
So go ahead and indicate the midpoint of the hypotenuse. Okay. Are there points out there that you say are equidistant from 2 and 1? You think? Yeah, it would form an isosceles triangle with the hypotenuse being the base. Paul, thank you. So it would be a diagonal line tilted perpendicular to the hypotenuse. And anywhere on that perpendicular bisector, the electrical force. Oh, wait a minute. You know what? I take that back. There is. Oh, Dr. B. You know what? There is only one place where it's 0. But that perpendicular bisector, there is something that zeroes out. So let's go ahead and make a note of this. See, I'm doing this on the fly, so I'm thinking with you guys at the same speed. On the and everybody's going to get correct on this one, so don't worry about that. On the perpendicular bisector, the net effect is going to be directed away from the hypotenuse, straight along the bisector. The perpendicular so the perpendicular components, perpendicular to the bisector, are 0. They zero out. But the components of the electrical effect along the bisector, along that symmetry line, yes, it is a symmetry line, they'll add together. So in the northwest quadrant, you'll have electrical effect pointing to the northwest. And in the southeast quadrant, on that bisector, you'll have electrical effects pointing to the southeast at whatever the tilt angle is there. All right. So those of you that answered yes are actually secretly correct on that one. But those of you that were thinking no because of the perpendicular bisector, good for you. You're thinking in the right direction. Yeah. Can I what? Can I draw it? No. I want you to draw it. I want you to go to the board over here. What is your name again? No, come on. I'll talk you. We'll coach you through it. Come on. What is your name again? Kristen. Go to the board. Kendra can stand right next to you. If you faint, she'll, Okay, so go ahead. And first of all, draw the triangle. Nice and big. Okay. Now one of them's shorter than the other. Okay, that's good. So drawing a charge up there. Okay, drawing your hypotenuse. Well, that's kind of a hypotenuse, I guess. Now, kind of visually estimate the midpoint and put a dot. What do you guys think? Is pretty good for a midpoint? All right. Now draw a line perpendicular at that point, right angles. Okay, go the other way to the north. Right. Well, okay, we won't. It's all right. She's not using it. She's not using a straight edge. You don't have to be Leonardo da Vinci II. Dude, don't mess up your fingertips with that ink. Right. That's good. So, so there's your perpendicular bisector. Now, can you take? Do you have a different color ink over there? No, something like a red. Is there a red marker over there? Is there a red marker around here? There's a Andrew. There's a red marker here on the. Okay, here you go. Go give that to Kristen. All right, now, Kristen, in the northwest, give me a red arrow pointing northwest. So put a dot somewhere on the bisector in the northwest, inside the triangle. A dot on the bisector. You've drawn the bisector. The line segment inside the triangle. No. You don't have to draw any more of it. You've got enough. That line segment in the triangle, inside the triangle. The bisector segment. Right. Yeah, just put a dot there. All right. Now put an arrow in red to the northwest in that direction from that dot. Okay. Yeah. Right. Now go down to the southeast quadrant and choose another dot. No, the southeast. Right. Any dot. And now give me a southeast arrow down there. Are you guys taking notes? All right. So now, which one of those dots is further out from the bisector? South. Kristen, you're not done. Okay, so the vector in the southeast is going to be a little bit smaller. So make the northwest one a little bit bigger. Erase the arrowhead. No, not your fingertips. Yeah, just make that one a little bit bigger. Okay, so it's probably going to be, it's a little closer to the area there, so it's probably going to be a little bit stronger. All right, and you can do the trig. You know, the trig is a menace to society, but you can do it. It's just sines and cosines and stuff like that. Now, the point here is this is something that we call a dipole, D-I-P-O-L-E. It's a version of a dipole. And thank you, Chris. Let's give Kristen and everybody else a hand. Paul, Thomas, and Krishna. Very good. That's a symmetry line. There's another symmetry line. That's, the hypotenuse. The hypotenuse is a symmetry line. And here's the nice thing. What was your name again? Cheyenne. The hypotenuse forms a symmetry line, and everything's going, everything's either going northeast, the same direction as the hypotenuse, or southwest, the same direction. If the field point is on that line or the extension thereof. All right. So, so those symmetry lines. Now, usually we don't draw a dipole like this. We draw it a little differently. But this is good to start with. All right. Now, let me get back to basics here. Here, of course, here's your answer. So here's the upshot of this. If you're on the bisector, if you're on the perpendicular bisector, so there's two symmetry lines: the hypotenuse and the entire line that formed by the hypotenuse, and then the perpendicular bisector line of the hypotenuse, perpendicular and right through the midpoint. So those special locations, if the charges are the same size, if it's proton and proton, then yeah, it'll be, but if one of them is +2 and the other one's +7, then you're going to get symmetry lines, but they're going to be a little different. But equal, yeah. And normally I'll write a dipole array horizontally or vertically, and then things are either x-axis or y-axis. But this one's a good exercise. Now here's the upshot. At that point, no matter what charge your apparatus has, positive or negative, if you put an electron or a fraction of a proton, if you put a quark there somehow, or a proton, no matter what, the electrical force will be zip zap, zero net force at that point. All right. So this thing here is nice. That's the Coulomb force between the charge number I. So I is equal 1 or 2, and Q app. That's the charge of your apparatus. I mean, that's how you do it. But we're not going to do that anymore. All right. So we're going to do the electric field, and here's how you abstract your apparatus out. This is how it shows up in the formula. It shows up this way. K times the charge, your source charge, subscript I, so however many I's you have, however many charges, so I equals 1 to 2 here in this case, divided by R squared, from your field point to your source point, and then R hat subscript I. Now, I'm going to show you how that works. Go ahead and jot that down. That's the electric field vector. Basic, basic, basic. Right? For as many charges as you have. So you might put a summation sign in front of that from I equals 1 to 20 if you have a big set of charges. This one, I equals 1 to 2, and you're done. So, so the net electric field would be KQ1 over R squared times R1 hat plus KQ2 over R squared times R2 hat. Now, let me show you the geometry that goes behind that equation. All right. So here's a basic example, Q7, charge number 7. And I've made it gray so that I'm not saying if it's positive or negative. All right. Now, the R hat vector, you can draw it at any point and in any direction. The R hat vector for number 7 always points away. It's a unit vector. It's sines and cosines. It doesn't have any, it has a magnitude of 1. Sine squared plus cosine squared equals 1. And it doesn't have any units, so it doesn't give any newtons. It just gives you direction. But and so if you want to put your apparatus out here on the x-axis, all right, at that point where the arrow is, good. That's the direction that you would use in that electric field formula, right? But look, you could, if you're up here on this diagonal, you pick a field point up there, no problema. It's still the same size. It's a different tilt. Go ahead and sketch that in. And maybe you got one down here in the third quadrant. Third quadrant's always tricky for trig. But yeah, it's just the same old deal. It's, you're a little bit closer. This is the closest point. The field point here for the third one is closer than the other two, looks like. And I just kind of picked random points to put these. Nothing special about them. And you could do it for any point. Here's another point. Go up to the, vertical, way out there on the y-axis, positive y-axis. Yeah, no problema. All right. Electric field's pretty easy up there for this point charge. So Q7 could be like -2 coulombs or minus 3.2 times 10 to the minus 18 coulombs. In other words, 2 electrons charges, or plus 7 coulombs, or 1.602 times 10 to the minus 19 coulombs. In other words, a proton. But the field line directions are going to come from these r hat vectors. Here's another one way out here. Right? So it doesn't matter where you choose it. You choose the point where you want to put your apparatus, then do the trig. And the directional arrows, there they are. This is for 5 different points, and you just choose whatever point you want. Right? And so, like if you're trying to do it here, electric field from charge number 7 is K times Q7 divided by the distance squared to that point times r hat. So here's your strategy. All right, at the point you've chosen, first figure out r. Okay, how far are you away from the charge? Okay, so this is the distance carried from Q7 out to that point there on the 30-degree line. And those are 30, 60, 90 all the way around. All right, so you get your distance, you square it, you put it in the denominator, and then you figure out your direction. That's sines and cosines for r hat. And then you figure out the magnitude, so then you do KQ7 over r squared, you do the quotient, and that'll give you newtons. All right? And so then you're done. All right, so now you've figured out the electric field vector at that point. Now there's no reference here to the apparatus that you're going to test with other than the location of it. So the geometric location, like the center of mass of your apparatus, for instance, that's all you need. And figure out r, figure out r hat, figure out the magnitude, and you're done. All right. Now let me pause for questions. Okay, let's continue then. Now I have some comments from my own, and also some comments from the textbook that I want to go over with you. And we got stalled by the hurricane, and I'm starting to get up to speed, and more and more I'll be mentioning my annotations and comments and readings for the textbook. So let's get down to it. Now the first thing is, my first comment is the field points in the direction that a positive test charge would accelerate. But if you have a negative test charge, or if you have a negative apparatus, then you just have a minus sign in the numerator of your quotient, and that'd mean your direction of your electric field is back toward the charge. So the charge, if Q7 is negative, the electric field vector would be pointing back towards Q7. But if it's not, if it's a positive charge, then it points outward in the same direction. It's negative, it's in the opposite direction to r hat. Okay. The electrostatic field, here's another comment from me. It's analogous to G for the gravitational field. We studied that last semester, or the previous semester when you were in 2053. The acceleration due to gravity at the surface of Earth. From the top of Mount Everest to the bottom of the Marianas Trench, the good old 9.8 meters per second squared downward. But that's actually the gravitational field. You probably didn't mention it at the time, but I'm going to show you why that is. Okay, so here's the gravitational force. If you're at the surface of the Earth, R is equal to R, and that circle with the plus sign in it, that's the symbol for Earth. So R subscript Earth. Quantity squared, because if you always measure it from the center of your object out to wherever your location is. So if you're at the surface, your location is R subscript Earth, and then quantity squared. In the numerator, Newton's constant G, the mass of the Earth And then the mass of your apparatus, little m. All right. Now that's the gravitational force. Now, I haven't put any vectors in there, but you could put them in there if you want. That's the magnitude of it. Anywhere on the surface of the Earth. Matter of fact, pretty close to anywhere from the bottom of the Marianas Trench up to the top of Mount Everest. R doesn't vary that much. The Earth is pretty big. It's about 6,400 kilometers radius. So going up 5 or 10 kilometers below the sea or above the sea, above sea level, it's not going to affect the denominator that much. All right, so the next step is abstract out your apparatus. Okay, that's M. All right, so we're going to abstract that out. And my wonderful students, you put those numbers in, G and the mass of Earth and the radius of Earth, it comes out to 9.8 meters per second squared. All right, and so that's what G is. All right, now you may not, I don't know if I mentioned it last semester in 2053, but I should have. And I'm mentioning it now for all of you, for everybody. All right. Now, another comment I want to make to you is from chapter 18.4. The electric field is defined in such a manner that it represents only the charge creating it and is unique at every point in space. Okay? It's not ambiguous. The way the force is ambiguous. You can have either, away or towards. You either have one of these or you have one of these. Right? But the electric field, only one direction because it's oriented to the source charge and not two charges. Right? So we've abstracted out the apparatus for the field. Second thing, also in chapter 18.4, and this is part of an example that I strongly recommend that you study. This electric field is the same at any point 5.00 millimeters away from the charge Q in the diagram there in the example that creates the field. So that's what you call another way of describing something that has spherical symmetry. So if you just have one point charge that you're looking at, spherically symmetric field, anywhere in any direction, you're going to have at same distance. So a circle or any circle, actually any sphere around the point charge, the electric field is going to be the same size. Although it won't have the same, it'll be pointing away, like a porcupine, quills of a porcupine. Now, I want to take a few minutes to do some demonstrations with you. Well, let me pause for questions on these comments here. Okay. I'm going to pause the YouTube here for a second. We're going to do some demonstrations. Okay, so just to review, we just went over two demonstrations, polarization and the electrostatic force because of polarization, and two, the Van de Graaff generator, VAN space DE space GRAAFF, two A's, two F's. Now we're going to get back to some more details about the electric field. All right, so let's get back to business with this. If you have a field point P, the electric field consists, the net electric field there consists of the electrical effect from the different sources, and they add up as vectors. And that's what this diagram shows. There's no target charge, there's no apparatus at point P. All right. So remember, we've abstracted the apparatus out. But to mentally think about the overall direction of the electric field vector, you can think, okay, what would a teeny tiny positive charge do at field point P? Left or right, up or down, whatever direction it will go. And then just remove it mentally from your thoughts. So let's keep going. Okay. Here's another way of writing the magnitude of the electric field, Coulomb's constant K. And for the magnitude, you just have the absolute value of the charge. For the direction, you need the sign of the charge, though. So you got to be careful of that. And then R squared, of course, down the bottom. Now, and here's something I want to emphasize. We're going to get into the directions here a little bit more. If the charge is positive, Q is positive, then the electric field vectors point away from it. They point outward. All right. So and that's because a positive test charge would want to move away from a positive source charge. So that Q in the middle, if you put a little teeny tiny positive charge, no matter what Q is at the center, if you went out on that equipotential surface, that circle, equidistant from the charge, you'd have the same size electric field vector, just a different direction. Right? And it would be pointing away. It would be pointing, go ahead and write this word down, radially away from the source charge. All right. Now, if you have a negative charge, the E vectors point the opposite way. Because if you had a negative charge in the middle, then a positive test charge anywhere out on that circle would want to go inward. Right. So, and the other thing I want to emphasize is that it looks spherically symmetric. So for the positive charge, the field is going to look like a porcupine, with or a sea urchin, right? The quill's pointing outwards. Okay, but it looks like a reverse porcupine if it's negative. So the field lines and the electric field vectors will be pointing inward. All right, and that's something to just keep that in mind when you're working on homework and stuff and studying. Now here's an example. Again, it emphasizes that all the surrounding charges contribute in whatever way their charge and their geometry indicates. So they both have different R's. Point P is a different distance from Q2 than from Q1. Q1 and Q2, they have their own sizes as well. So, and one of them's pointing, E1 is pointing to the right, E2 is pointing to the left. They're both positive. Right? So the field from charge 2 points to the left. The field from charge 1 points to the right. Okay. Now let's try a variation of that. Here's another diagram. And click a question. This is multiple choice. Calculate the size of the net electric field at point H. Okay, so there's an electron and a proton. Okay, so the charge, is the charge still up here? Can you write down the charge of the electron? E equals 1.602. And can you write down K? K equals 9 times 10 to the 9. Newton meter squared per Coulomb squared. So work that out with your neighbors. And you better use your calculator. By the way, when we do these calculations of, now, and by the way, the unit is newtons per Coulomb. It's not newtons anymore. So when you do this, you're going to have newtons on the top and coulombs in the denominator for the units. That's all right. That's normal. And it's actually going to be meganewtons when you do this carefully. And don't forget, 4 nanometers is 4.0 times 10 to the minus 9 meters. Just saying. My famous students with the awesome hair. Man, you guys did great. Everybody did great. Now, I made this so it's fairly cinchy to calculate. Anytime you have 4 nanometers, it's quantity squared in the bottom and 1.602 on the top. It's going to be pretty cinchy. But then you have 9 times 10 of the 9 Newton meters squared per Coulomb squared. Yeah, that's right. Don't forget, Kendra, I want to know everything you can tell me.
Okay. Yeah, we're having someone come in and talk to us next Tuesday, but last night was basically more introducing. Sorry about the hurricane and
Mm.
nonverbal things that we can do to make students feel less comfortable and asking us questions.
Did they tell you about the 15-second rule?
So wait, like ask them a question, then wait till it's basically uncomfortable.
No, wait till it's always wait 15 seconds. That's what I do.
He told us wait until it's uncomfortable, until there's an uncomfortable silence, and you need to say something.
Yeah. Yeah, it's the 15-second rule. That's the way I learned it when I was a grad student, my first year. This is pretty cinchy because there's a lot of duplication here. Did you guys notice that? Better write down the charge of the proton and Newton's Coulomb's constant in the inside of your inside front cover of your notebook or something, because we're going to use them a lot. Oh, by the way, I have office hours today at 12:30 to 1:30 over in room 158 in the physical sciences building. And Kendra is going to be there 4:30 to 5:30. So if you want real expertise from an undergraduate, 4:30 to 5:30. But if you want to talk astrophysics, 12:30 to 1:30. What's that? That's pretty good. Laser seminar, 4:30 to 5:30. That's good. What's your status, Andrew? No. Well, yeah. What do you study?
I do ask
Asteroids? Sweet. Who's your advisor? Very good. Good, good, good. So you don't, are you doing any planetary defense type stuff?
Not directly.
Like, did you see Dr. Fernandez on the news this morning?
No,
Yeah, Channel 9 Eyewitness News. Yeah. Using Arecibo to find near-Earth objects.
Yeah, we do mostly further stuff on here.
So you're out there in the ozone layer. Yeah, Dr. Kempines.
Yeah, he does been there.
Yeah, no, that's all right. Yeah, I had a TA a couple semesters ago. Let's see, spring of 2018, and she was I can't remember who. I think she was working with Dr. Britt, and she was modeling comet and asteroid impacts. So she was trying to contribute to planetary defense. You've heard of the Homeland Defense Department?
Yeah.
One of these days we're going to have planetary defense. And when that comes, they're going to be looking for talented guys.
It is important. There's a lot of
General Andrew.
I worked at Northrop Grumman over the summer, and when you said it's good enough for government work, I was like, oh my
Boy,
God.
I tell you what, that's a thing. Do they say that a lot over there?
They don't. They're just like good enough, and I'm like, oh, is it? No.
Yeah, yeah.
My labs are like, to the fourth decimal place around this,
Yeah.
and they're just like, just give me the whole number, and I'm like, I don't know about that.
Yeah, you know why that is? Because were you working on classified stuff?
Yeah.
Well, that's why they didn't want you
I didn't get.
becoming too much of an expert.
Yeah.
Did you have a security clearance?
No, they offered me next summer, and they offered me the highest degree, but I haven't accepted yet, so I'm still on the same. But this time I just had to sign an NDA.
The no blab agreement.
I don't know. I was in California, so I don't know if I want to go out there again.
Oh, no way. No, California, too many earthquakes.
And
That's,
I was there during the biggest earthquake they had in 20 years. That's where I
yeah,
was.
I,
Yeah, I was there.
yeah, I interviewed for a job out there in Burbank, and I went, but I decided I didn't want to take any
It
job
was
out
nice
there.
because I was like jogging distance from the beach, and then I went to like a bunch of national parks, and we have every other Friday off, so I get a long weekend to go camping every other
What?
weekend. It was great, but like it's so expensive,
Yeah,
and I don't know, it was really far away from me. I was alone out there. No one from university could afford to live
yeah.
there either, so I was just kind of like bored.
20 seconds to vote. Well, it's not boring once you get into it. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys have got. Uh-oh, we got some splaining to do. Um, we got a little bit of difficulty here. Uh, look, the Q over R squared is basically 1 times 10 to the something. All right. So the numeric part is going to come from K. So you got 9 times 10 to the something for both of them. And they're both the same size. Why? The P is pushing to the left and E is pulling to the left. They're both, so directionally you have 2 times 9 times 10 to the something. So that's either 18 or 180 or something like that. And in this particular case, it's C. Yeah. So double check. Now I'm going to give you another question here. Wait a minute. Hush now. It's almost time to dismiss. Um, make sure you know how to do this. Jot down the answer and make sure you review if you didn't get it right. We'll dismiss after this question. So go ahead and answer this one. And I already gave them the answer if they remember. So, oh, okay. Wait, no, wait. No, that's the other class. All right, here's the question. Okay, now that's the question. Okay, you better get it right. Anyways, you're dismissed after you click. I'll see you on Friday. No homework, but homework is coming. All right, let's just wait for everybody to click in here. Okay. Um, I